The previous video cut off when we were working out this problem, and actually I found a little error here that's going to prove to be important. This one is supposed to be a 2. That's supposed to match that. Why is that important? That's going to be a 2, and now when u is natural log of 2 here, not natural log of 1, that's going to make our life better because otherwise we'd be dividing by 0 here and we'd have a doubly improper integral, and we don't want that. So let's take care of this. When we integrate 1 over u squared, we get minus 1 over u. We end up with 1 over natural log of 2 minus 1 over r. And what do we end up with? This is, as r goes to infinity, that goes to 0. So that's just 1 over natural log of 2. So this converges. So by our improper integral converges. So this converges by the integral test. Okay, so let's look at, that wraps up our discussion of the direct comparison test. Now let's look at our final test, the limit comparison test. So suppose that we have two sequences an and bn that are both positive sequences, and suppose that the limit as n goes to infinity of a sub n over b sub n exists, or is infinite. So if the limit is anything between 0 and infinity, then the sum of a sub n and the sum of b sub n have the same, they behave the same. Either they both converge or they both diverge. So that's the best case, if the limit is anything between, strictly positive but not infinity. If the limit is infinity, then we only get one direction. We only get that if the sum of the a sub n's converge, then the sums of the b sub n's converge. If the sums of the a sub n's diverge, it doesn't tell us anything about what the sums of the b sub n's does. And then finally, if L is 0 and the sum of the b sub n's converge, then the sums of the a sub n's also converge. Again, if L is equal to 0 and the sums of the series for the b sub n diverges, it doesn't tell us anything. So how does this look like in practice? Well, we're going to kind of approximate. We're going to approximate series with, terms of the series with other terms. So we've got n squared over n to the 4th minus n minus 1. And so we kind of ignore the smaller terms here. The denominator is really approximately n to the 4th. And so n squared over n to the 4th, that's like 1 over n squared. So the thing that we're going to do is to use our limit comparison test. We're going to say an is n squared over n to the 4th minus n minus 1. B sub n is 1 over n squared. And so when we figure out the limit as n goes to infinity of a sub n over b sub n, so the limit is n goes to infinity of n squared over n to the 4th minus n minus 1, all over 1 over n squared. And so this ends up as, the limit is n goes to infinity. After we move that 1 over n squared all the way up to the top and divide top and bottom by n to the 4th, we get 1 over 1 minus n to the minus 3 minus n to the minus 4. Those go to 0, and we're just left with 1 here. Okay, so the limit here, this is our L. And so we are in the case where L is 1, so L is between 0 and infinity. So this tells us that the series for AN and the series for BN have the same behavior. And we know that the sum of n equals 2 to infinity of 1 over n squares, this converges by p-series test. P is 2, that's greater than 1. So by our limit comparison test, this series also converges. So how do we apply the limit comparison test? We approximate, we kind of take the most important terms here. These are unimportant, so we say terms here are about n squared over n to the fourth. That's 1 over n squared. We calculate a limit to make sure everything checks out the way we want it to check out. We get a limit that's between 0 and infinity. And in this case, these two series have the same behavior. In this case, they both converge. One last case here. How about this one? The sum from n from 1 to infinity of the square root of n squared plus 4, 1 over the square root of n squared plus 4. And so if we ignore this plus 4, we've got like a square root of n squared there. So the square root of n squared is n. So we're going to take a sub n is going to be the original, 1 over the square root of n squared plus 4. And bn is going to be 1 over the square root of n squared, which is 1 over n. Everything here is positive, so we can do that. So our limit, as n goes to infinity, a sub n over b sub n, is going to be 1 over square root of n squared plus 4 over 1 over n. And so the limit as n goes to infinity of n over square root of n squared plus 4. We divide top and bottom by n. We get the limit as n goes to infinity of 1 over square root of 1 plus 4 over n squared. And once again, that's 1. So because this is between 0 and infinity, we are once again in this first case that the two series of the a sub n's and b sub n's have the same behavior. And since the sum from n from 1 to infinity of 1 over n diverges, we know that's the harmonic series. So does sum from 1 to infinity of 1 over square root n squared plus 4 by the limit comparison test. So that's one last example for us to look at.